Swayam Prabha. Digital India. Educated India.
So it's good to see you all again. As I say, most of us are back, but not quite everybody. So the plan today is to really focus on energy systems all day. I'm going to talk for a while. We've got a guest speaker, and then this afternoon we're going to do a role play simulation to think about providing enough electric energy for a city to maintain reliability, but also thinking towards renewability. So how many of you work closely with energy systems of some fashion? All right, so I just always like to know where to. So I'm going to give you some overview. Please, as always, if you have any questions, feel free to interrupt me as I go. It's always hard to know how to aim, what level to aim the talk at. So first of all, why are we going to start with energy systems? We just did 2 days of introduction to sustainability, circular economy, life cycle assessment, just to give you the background and the overview. And now we're going to spend days on energy, water, end of life. Why start with energy? Right. So in reality, energy use is a main cause of greenhouse gas emissions and a lot of other environmental impacts as well. So it's not just greenhouse gas emissions. We often think about that first, but it is a major cause of our environmental degradation and therefore also social, especially public health impacts as well. So it's really important. So I think we start with priorities and just some of the, yes, it's climate, greenhouse gases in the middle there, but there's all sorts of other factors that have an impact on things that are related to energy use. All of those words in some fashion have some aspect of energy system. So it's also pervasive, right? You can't get away without thinking of energy, either energy used to create the materials, to manufacture, energy in its use, implications of energy, maybe energy recovery and its end of life. So it is throughout the entire life cycle assessment. So all countries, according to the United Nations Convention on Climate Change, now do greenhouse gas emissions. I'm going to share with you some US and India statistics here. But just to give you some idea that this shows, so this is 2021. It's the most recent that's available in the United States. Just a couple of terminologies. It's million metric tons. When you see that. And so in the United States, our energy systems between transportation, electric power, and even most of the industry, not all, come from our use of energy. Almost all of that. And most of the energy results in the formation of the greenhouse gas carbon dioxide. That's the direct result of combustion. There's also methane, comes from both our energy systems as well as our agricultural systems. But a big chunk of it does come from our energy systems. So when we think about your answer is spot on, from a greenhouse gas perspective, the ways we provide energy, the way we use energy is most critical in terms of greenhouse gas emissions. When we look at India, the most recent that I could find was 2018. And again, so this circle here, 83% of the greenhouse gas, India divvies it up a little bit differently. They don't break it down between transportation and electricity, but still our energy systems, 83% are due to our energy systems. And they break down a little bit. IPPU at 7% is industrial processes and product use, and AFOLU agriculture, forestry, and land use changes. So you can see energy is really important. And similarly, it was 79% in the United States and 81% of the greenhouse gases emitted in India are carbon dioxide. And that's largely from the energy use. So it's big. It's big, at least in terms of greenhouse gas emissions. And we quantify this, right? We go through all the processes from extraction through end of life and use. We quantify greenhouse gas emissions, a lot of other emissions from our energy sources as well. So just to think about just your lives this morning, how many ways have you used energy this morning? Alarm clock. All right. So electricity, right? Or battery or battery. All right. So that is one way to store and then use. Charge your phone. Was that electricity? Okay. Water heater. Okay. How is water heated? Do you know? Electricity. All right. Anybody else? The water. Okay, so good. You're thinking upstream. So water you use, how, even if it's cold water, right? Tap water. Where's the, okay, so if it comes from groundwater, there's pumps. Treatment processes use a lot of energy, mostly electric energy. Okay. Transportation. What did you do for transportation? Mobility. Okay, I walked. So I used energy, right? That used energy, but that was my breakfast that I was using. How did you get here? Put petroleum on a bike. Okay. Cooking. Okay, so induction. You have induction stoves here. Is that standard? Induction stove? Is that what you said? Yeah, yes. But is that the standard way that an Indian stove works? No. Oh, okay. Gas? The cylinder gas. Okay, but induction stoves are really highly efficient. So you got to have different pots, but they're really, really, really efficient. But okay, so there's a different form of, right, liquefied petroleum gas, right, or something of that sort in a canister for cooking. So it's pervasive in our lives. And there are other ways. So the embodied energy, right, like in the water, the energy that somebody else provided and added to that water in order for you to have water that is at least clean enough to bathe in, if not drink in. All right, so we use it. So whatever we're looking at for a life cycle assessment or industrial process or a product, there's going to be energy in there some fashion, either upstream or downstream. So what's really most important is to think about the systems and the energy systems that we are going to look at. So first of all, we have primary energy sources, but then we also have energy carriers. And some people, like electricity, is not an energy source, right? That is an energy carrier. Unless it's lightning, maybe, but electricity is not an energy source. So our primary energy sources, that's solar, wind, coal, fossil fuel, nuclear power. They are things that have like chemical energy embodied or mechanical energy as part of whatever the material is, right? Coal it's a chemical energy. You combust it, it's an exothermic reaction. But then it's not that convenient to use coal. I know that there's still probably industries in India that use coal directly, but you in your everyday life, you don't use coal, right? Even cook stoves and more and more are using liquefied petroleum. But the easier way, and what many of you say, is electricity. Electricity is so convenient to use. So that's an energy carrier. So we have some conversion processes like thermal power plants in that middle picture that transforms the chemical energy in the coal or natural gas into electricity. And there's a whole series of processes to do that. Then we put it on our transmission and distribution lines to get it to you wherever it is most convenient for you to use it. We use it, and then you're a user, right? So the consumer is part of this system too. If you don't turn things off, then you are part of the even turning it on or off, you're part of the energy system. We also have natural gas, or which liquefied petroleum gas. Same, so it's a different type of extraction. They're still refining. This is a picture of a water heater. In the United States, a lot of the water is heated with natural gas instead of electricity. And there too, your shower, if you take really long, hot showers, then that's going to be a lot of electricity. So there's all sorts of these systems, but they always start with there's some primary energy source, and there's some consumption somewhere at the end we're involved, and there are any number of conversion processes in between those two. So when we're talking about energy systems, we're talking about all of this. So when we think about energy resources, this is like the one of those impact or indicators, impact categories or indicators that we use in a life cycle assessment is the use of natural resources, right? Those natural resources that might be abiotic and limited in their, right? There's only so much coal and natural gas in the world. Then we have some refining processes, and we have energy use. We also have our renewable systems. Most of the renewables get used to formulate electricity. Biomass, though, sometimes goes directly to transportation or heating. So there's other uses for biomass fuels. But the solar, the wind, hydro, nuclear is not technically a renewable, but it is a very low usage. So that they all get used to make electricity. So often people say energy use when they really just mean electricity. So we've got to keep separate, right? Keep track of electricity is not the whole only, right? There's other forms of energy that we use, and it's predominantly transportation, maybe heating, if that's, or cooking, if it's coming from, so energy does not equal electricity. Electricity is a component of energy, but not everything. So we've got all these things. We've got this primary resource. We've got conversion processes, and there's an awful lot of engineering and technology in that. And then we've got our users. And you've mentioned a lot of these uses already, right? So nobody mentioned the AC, but we are all using AC this morning, right? That is electric energy use that can be more or less efficient depending upon the technology used, but it keeps us comfortable, right? So a lot of this is about our convenience and comfort and our mobility, our ability to get different places, our ability to have food that can be refrigerated so that it is safe for us to eat. So it's, you know, very human-centric. All right, so this is the United States. On the left are all the different primary energy resources that are used in the United States. You can see petroleum is the biggest, natural gas, coal. So if you look at those fossil fuels, they're a pretty big chunk. And this is all energy, not just electricity. And over on the right is all the different ways we use that same energy. And in reality, because we don't generally store energy for long terms, right? We can store it for short terms with a battery. We saw that if you make hydrogen, that's a longer term storage. But generally, these numbers are annual numbers, and I'll get to the units in just a moment. But the left has to equal the right. Generally, there's not a lot of, and this also includes imports, not just within the geopolitical boundary of the United States. But we have to, what we combust in one way, we use in another way. So this comes up. So the left hand and the pink columns are still the same. Now I've got added a all bunch of lines. So this is called this Sankey diagram. Has anybody seen one? A few of you have seen a Sankey diagram. It sort of is, and these are not just used for energy systems. It shows on the left the sources and how they're used. And you can see that our different energy resources go in a lot of directions. A couple of things that are easy to note is that most of the transportation fuel in the US is petroleum, and most of the petroleum goes towards transportation. Natural gas is a very flexible and useful fuel. It goes to electricity, it goes to industrial sources, it goes to residential and commercial sources. So it goes all over the place. And electricity here, it's in its own column, right? It's not a primary source. It's not a use, but this is our conversion to make it an energy carrier. So I'm going to pick apart this diagram, and we will also talk a little bit about this column. It's not all useful energy, humanly useful energy. I'm going to pick apart and just look at pieces of this for a minute, since this is a little too much to comprehend in the first look. So key, we've got total energy use, some fraction of that's from fossil fuel, and then we've got electricity use are all really important components. So let's just look at that electricity generation. So I scrubbed everything else. So you can see electricity generation, this is in the whole United States. Some amount of it, so I should define this. A quadrillion is, let's see, 10 to the, not 10 to the what quadrillion. So that's four sets of three zeros. So what number is that? Yeah, 10 to the 12th, which is also a tera. If you were in a metric system, it would be a tera. That's what I was looking for. Yeah. So a quadrillion BTUs, are you familiar with BTUs? Okay, so yeah, it's just a different, the way, like one BTU is if you have a small wooden match and you burnt that all the way, the heat generated by a small wooden match is about one BTU. So we're talking a lot of wooden matches here, but we don't need to worry about. Anyhow, so in the US, we use BTUs. So my apologies for that. I was not going to redo all the units here. Nuclear is the other big input into our electricity generation. But what's important is only of the 37.7 quadrillion BTUs, or quads is the way we refer to it, we only get 13.3 quads of useful electricity generated. The rest is what we call rejected or wasted heat. It's not lost, right? It's still in the system. What forms of losses? Anybody have any ideas? Heat, absolutely. When we combust, we generate heat as well as electricity. Anything else? I heard transmission losses. Okay, that comes downstream. But yes, we do have transmission losses. They are part of that. Leakage of, okay, so that would be on the left-hand side. But yes, so somewhere in here, it doesn't all get there, right? There's some leakage there. So, and that's because of heat. Noise, right? Noise is a form of mechanic, all these equipment, right, are noisy. So if you hear noise, that means that's some inefficiency. Vibrations, that's a form of inefficiency. So it's turning to mechanical or heat energy instead of electric energy. So just all different forms of energy, but they're not all useful to us. So when we talk about efficiency, we're talking about those forms that are useful to us. Sometimes we can capture and use the heat, but we don't always. It's really hard to capture and use vibration or noise, although some people try to capture vibration. And so we often use this efficiency, which is the useful energy out over the energy in. And overall in the US, it's about 35%. So it's pretty low. That means a lot of the primary energy in is not getting used in a form that's useful to us. So that's a critical message about our energy systems. And so in this case, the US fossil electric is 57% renewables. All right, where did I go here? I already did that. All right, so now if we look at the whole thing, um, renewable energy is about 13%. This is overall for all uses. So most of the renewable energy is used for electricity. Some of it's used other cases, but most of it goes into that electricity. And then we already talked about the 35% for electricity. Transportation is even less. Internal combustion engines are notoriously inefficient. Diesel engines are a little bit better, but very inefficient, only 21%. And so in this case, we see most of it's rejected. And you can tell that, right? Your car vibrates, you idle, right? So you're not moving, but you're still consuming gasoline. It gets hot, right? Those are all forms of inefficiencies in an internal combustion engine. Electric vehicles, in part, are better for the environment because they're incredibly more, an electric motor is much, much more efficient than an internal combustion motor. It's not just what we're putting into it, but it's just the overall, the system, the conversion system to make mobility is far more efficient in an electric vehicle. So overall, we have about 33% of the primary energy used in the United States results in something that is useful to human beings. Not very good, right? If you had material use of 33%, if you were cooking dinner and only 33% of the food that you had ended up getting eaten, right? That's not very efficient. You would say, oh, that's horrible. But that is, and part of this is thermodynamics, partly it's just a really big, complicated systems. We've got leakage everywhere. All of those sorts of things are important in these systems. So this is India. And so it's also a Sankey diagram. So the units here are million tons of oil equivalents. And so that's just a megajoule to megajoule comparison. So like a gallon or a liter of oil has so many megajoules of energy, then they put everything on the same basis as that. So it's just a way to compare the different energy intensities of these different fuels. So what do you see on here that might look different? Anyone? I'll just go. So I'm going to ask that question again. So I'm just going to go back one. So here is the US. Okay, so renewable is very small. High use of coal, very high use of coal. Anything else? Hydro is in here. This is hydro. Yeah, so it's small. It's there. Nuclear is there as well, but it's small. There's no geothermal. There's no geothermal. There is one in. So geothermal, are you talking about heat from the earth? Yeah, heat from the earth. Do you use heat from the earth? No. If you're in Iceland, Iceland gets to use heat from the earth, right? They're right on top of volcanoes. They make almost all their electricity from geothermal steam. Steam comes right out of the ground. All right, so lots of coal. One of the things that I thought was interesting is that much smaller fraction of the oil goes into transportation, right? In the United States, almost all the petroleum products went into transportation, and you use it in many more different ways than is used, including in cooking. And some of the exports and imports are accounted differently here. But coal is a hugely different, much higher use. And so in this case, if you look, there's a couple of things on here I can show you. So this is electricity, and it's in units of MUs. And I could not figure out what is a unit of MU. Electricity generation? Anybody know? This is what your government tells us. MUs. Units, right? 1 kilowatt hours a U? A U, okay. So this would be million kilowatt hours. All right, thank you. I could not find that in any of the reading I did about your energy system. But yeah, so coal is 73% of your electricity generation. And I didn't identify all the other bars, but you can sort of tell it's almost all coal, but we get a little bit of renewables with the green, the different color schemes here, hydro, nuclear. So there are some other things, but it's mostly coal. And that we will come back to that. So India looks a little different. Overall, whoops, I thought I did this math. The Here we have the losses. I did this math, but I don't seem to have put it on my. So you can calculate the efficiency of the electricity out over the electricity in. And it seemed like it was maybe a little bit higher efficiency than in the US, but I don't remember that. All right, so why do we have these inefficiencies? And thermal power plants, coal, natural gas, anything, is a very inefficient process. And part of the problem, and I asked this question at least in batch 2, people who were doing the tour, like the more different pieces and parts that you have of your energy system, the more potential there is for inefficiencies. And the overall inefficiency or efficiency is the product of the efficiencies of these components. And so to make electricity, so this is your coal source, your coal chamber. You have your boiler burning coal. So transforming the chemical energy in the coal to the thermal energy in steam, 85% efficient. And then we have a steam turbine. And so you're making steam that's driving a turbine, which then is making mechanical energy, right? It's rotating energy. That's only 45% efficient. And then to make the generator, we've got magnets and copper coils that get spun from that turbine. That's what then makes the electrons in the copper vibrate. That's what makes our electricity. 95% efficient. So if you multiply all of those out, we get 36% efficient. So you can see the biggest challenge here is in the steam turbine. Does anyone know any other systems? Anything else? And a lot of that is heat loss. There are gas turbines, which are more, so often natural gas is more efficient. And they have combined cycle. There's all sorts of technologies happening to try to improve mostly that piece there. It's the biggest source of losses, but there are losses along the whole way. And even getting from the coal plant to this taxi, that's only about 80% efficient, right? You have losses at the mines, you have losses in transporting it, you have losses in pulverizing it and getting it ready to put into your coal-fired power plant. So efficiency is a biggest challenge with our energy systems, and I just wanted to explain that a little bit. All right, so now we just looked at a green system the other day. These numbers are not the numbers that are appropriate for that. I was just looking for some sort of numbers to have some sense of the system that we saw in the research lab the other day. So we had solar PV stored in a lithium-ion battery. It was used to electrolysis to make hydrogen, and then the hydrogen was put into some kind of a fuel cell. I am guessing it was a proton and exchange membrane. I don't know. That's the most common, so I guess. So I just looked up typical efficiencies for all of those different systems. One of the biggest challenges is of all the sunlight that hits a solar panel is very low conversion into electricity. But that's sort of a freebie. So lithium-ion batteries, initially they're sort of between 74 and 88%, but they also decline in efficiency over time. So this is sort of the best case. Electrolysis, about 70%, and the hydrogen fuel cell, I thought they were more efficient, 40 to 60%. So if I multiply out all the smallest numbers or all the biggest numbers. If you don't count the solar PV, only 28%, we're at 21 to 37% efficient. So it's really not that, it's about the same in terms of efficiency as the thermal power plant, but the difference is that it's solar, right? It's not coal that is the primary source of energy. So the improvements in that regards, but it would be really interesting to see what their actual numbers are for efficiency. These are just, what I could find in 20 minutes of reading papers about these kinds of systems. So I just wanted to give you some idea that here too, the more component parts you have, the more chance there are for inefficiencies. All right, so back to environmental impacts. So we've got and now I'm just going to mostly talk about electricity for the rest of this talk. So we've got the big picture there. Greenhouse gas emissions, we already talked about, are one of the key reasons that we pay a lot of attention to our energy systems. Coal, even compared to gas, even if they were the same efficiency, coal generates by far the most. So these are tons of carbon dioxide equivalents per gigawatt hour of electricity generated. So if you have coal-fired power plants, then it's going to be mostly coal. So it's mostly times 970 tons of greenhouse gases. And obviously the fossil fuels are much higher than anything else. Biomass does generate greenhouse gases, right? So combustion of carbon-based fuel. Now, sometimes you can negate some of the photosynthesis, right? If it's recently grown biomass, then that took carbon dioxide out of the atmosphere last year and it's putting it back in this year, so it's somewhat net zero. But if you're cutting down ancient trees and then you're combusting them, that's just as bad as fossil fuels, right? Or even if they're decades old trees, then that is adding relatively new carbon dioxide into the atmosphere. Solar, hydropower, wind, and nuclear, these are life cycle greenhouse gas emissions. So even though when you operate a solar PV system, you're not generating greenhouse gases right there, you still had to make the equipment. And so if you average that over the lifetime, or wind, there's a lot of metal in wind turbines, that contributes toward the life cycle energy emissions. So they're not zero. We often treat them as zero because we're only looking at the combustion, that conversion. But they're tiny compared to the coal and natural gas, but they're not non-existent. So greenhouse gas emissions are very substantially. But we don't ever use just one of these, right? So we often use a mix of different technologies to make our electricity grid. So these are some pictures from the United States and the top. So these are in pounds, not the others were kilograms, tons. So that was 1,000. Anyhow, I did not convert these either, but you can see at least relatively. So nationally, about 60% fossil fuel. But remember, this is the natural gas. This is half of the greenhouse gas per gigawatt hour compared to this coal. So it's that coal that really racks up the greenhouse gas emissions. I live in upstate New York, so it's everything from, I don't know, 100 kilometers north of New York City and the whole rest of the state. We have very little fossil fuel, about 25% natural gas and no coal in the generation in upstate New York. A lot of hydro and not a lot of nuclear. Hydro is on Niagara Falls and the St. Lawrence River, really big hydro, and lots of little hydro as well. And then this is New York City. Is almost the generation in New York City is almost all natural gas, but they import a lot. So that they don't generate very much, but what they do generate when they have like a really hot summer day and everybody turns their air conditioners on, it's all natural gas. They used to use a lot of residual oil as well, but it's natural gas. So New York City is generation is natural gas. So that was one environmental impact, life cycle environmental impact of our energy system. So land use. So this all was, I got from a presentation I recently saw at Clarkson about nuclear power, and I'll get to that in a minute. Solar, ground mount solar is by far the highest. 19 square meters per megawatt hour. So that's a lot. Nuclear is very small, and that's what this was trying to promote. Wind turbines, they're saying 99 square meters, but if you look at that picture of a wind farm, there's a lot of other land use happening too. So I think that that is artificially inappropriate. There's a lot of forest and agriculture land often mixed in with wind farms, at least in the US. But the solar farms can really, really consume a lot of land space. So that's ecosystem, food generation. So there's a loss to that, right? It's clean electricity, but at a loss. Materials intensity. So how much mass of stuff goes into these systems. Offshore wind is by far the highest. Huge towers and huge underwater infrastructure as well. So the infrastructure for offshore wind is, and then you've got to get the electricity to land as well. Solar PV is high as well, but largely it's steel. Steel is big. There's glass is a big part of the solar PV as well. And of course, this was promoting nuclear to show that nuclear is very small material intensity, at least the newer nuclear power plants. And that's a picture of a copper mine. We don't often think about copper and some of the metals in our electricity system. It ends up being really important from a life cycle perspective, all that copper that gets used in our electricity infrastructure. And then if we put fuel and material intensity together, coal, we've got to dig out all that coal. So huge amounts of coal. It gives us, it is a material, but it's also the fuel, methane gas. And nuclear, only 22 grams of uranium are needed per megawatt hour. So it's really tiny, although you had to do a lot of mining, right? So the ore that was mined would be much, much higher. So there's all these different ways to think about our energy systems. And clearly, except for land use, the fossil fuels are the worst actors in all of these. And this doesn't even talk about the other pollutants that we get when we combust fossil fuels. So we just talked about greenhouse gas emissions, land use, material intensity, fuel intensity. What else are the environmental impacts? Water, okay. Anything else? Do any of you live near one of the coal-fired power plants nearby? Air quality. So what is it in the air quality? You're absolutely right. Particulate matter is huge. So particulate matter either less than 10 micrometers or less than 2.5 micrometers. But we also have NOx and SOx. We introduced those the other day. They create acidification. NOx also contributes to smog when you also have VOC. So air quality is huge. Anything else? Radiation, yep. Which is a human health issue. All right, so I just want to share with you some, this is a student, my student who's graduating in just a couple weeks, looked at Northeast United States. So this is more than just New York State, but we were looking over time. So from the electricity mix in 2010 to what's proposed for 2040, with heat pump for heating and cooling. And so for climate change, you can see over time, and I'll get back to this again, my circular thinking here, we'll have a lot more renewables by 2040. And so you can see the greenhouse gas emissions go way down, but almost all the emissions are from the electric grid and not from the heat pump, including the refrigerant in the heat pump. So the greenhouse gas emissions go way down. But at the same time, toxicity has a tendency to go way up. And again, so once we get towards a renewable electric grid, that is largely due to the metals and all the toxicity related to metals. So people often just, we focus on climate change so much, we forget that there are other, water use is another good one, that there are other impact categories that we need to land use with the solar panels. So there are trade-offs, right? This is not all a win-win when we think about going to renewable energy. But toxicity is something that we don't talk about. So I just want to, this blue part, one of the things that we discovered in the life cycle assessment modeling that we did, we'll talk about this more next week, but the database that we used in EcoInvent, which was the most widely used database for electricity, even for the US, Northeast United States, they assumed that the copper at the end of life was being incinerated. And they were putting that copper into the atmosphere. This came from like a 1990 Swiss life cycle assessment. Well, maybe in Switzerland in 1990, they incinerated their copper. It is way too valuable, monetarily valuable, to think about incinerating it. And so that part of the blue is just like, this is not a relevant component in the Northeast United States. So we didn't want to totally take it out because we don't have alternative life cycle accurate data for recycling, but we know we're not incinerating it. And it had a huge impact on the toxicity. So you got to be careful when thinking about life cycle assessment. But it is the infrastructure. The toxicity comes much more from the electricity infrastructure, transmission and distribution, and all the metals used in wind power and things of that sort, rather than the actual conversion of electricity. All right. So, yeah, biogenic carbon. It goes back to Professor Indu's talk on the first day. It depends upon the carrying capacity and the capacity to renew the carbon. So when you combust biomass, carbon dioxide, and a lot of particulate matter, it's dirty burning, even compared to coal, are released, right? So we're putting carbon dioxide into the atmosphere. But that carbon dioxide, if you grew, let's say it came from some fast-growing switchgrass or bamboo, photosynthesis made it come out of the atmosphere, right? And so there's more of a circular economy, circular. It's going out, we're generating carbon dioxide when we combust it, but then we're taking it back up when we're growing it. Fossil carbon is coming out of the ground, and that's all just getting added to the atmosphere. Did that answer your question? Yes? Yes. Okay. Sorry. To me, this is no. And I know that, but it's still hard for me to remember. Okay. So that answered your question. Yes. Thank you. Okay. I actually, Indu taught me that. The first day I talked to her, she just kept doing this. I was like, oh, how am I going to communicate with her? She doesn't understand anything I'm saying. It was a lesson to me in my cultural diversity. Okay. So let's talk globally for a little bit. I talked about India, United States. We're going to come back to United States, especially New York State. This is global 2020 total energy consumption, not just electricity. Moving forward, this is part of the Paris Agreement and thinking about keeping our temperatures not more than 1.5 degrees above pre-industrial revolution. We need to do substantial decarbonization. And that means that it's not that we're going to use no fossil fuel, but it's going to go from the largest percent of our global energy to a very small percent with a lot of renewables. So this projection was well, this 2021. I haven't seen, and so it's showing less energy generated because we're also going to be more efficient, right? So if you're more efficient, then you just need less energy. What has happened since 2021 to 2025 that does not mean that our constant energy is what's happening that's consuming a lot of energy? AI and data centers, right? So in reality, we probably need this much energy, right? Here's our AI, and I'm guessing, which were not comprehended just 4 years ago, the impact and the rapid growth of this. And so all of the models that show projected energy to meet the Paris Accord and, to meet that 1.5 degrees, they did not include this, which is kind of scary. So somehow we've got to have more other renewables or nuclear or hydro or things of that sort. But this is the number one idea moving forward is we have to decarbonize our energy system. If we just look at electricity, this is where we're showing a lot of growth in the demand. But this is more because we're going to electrify our systems. So in the United States, that means electric vehicles. It means heat pumps for heating and air conditioning, which are now electric rather than combusting natural gas for heat. It means induction cook stoves rather than natural gas in our cooking. So if we operate everything on electricity, then the electricity demand will go way up. And the idea is that most of that will be solar and wind. So this is sort of the change. And again, there's still a little bit of fossil fuels, but the idea is that it goes way, way down. So these are key things to think about the future. So when we're doing life cycle assessment, and that's what the student that I showed you, trying to figure out how to project into 2040, we anticipate what the electricity mix will be in 2040 and then model that with some inaccuracies, but lots of changes in both total energy and electricity. So I'm going to introduce a little bit about New York State. New York State has very progressive climate laws. Still moving forward with these. The country has regressed some, but New York State has not. And in part because this will also be useful for you this afternoon in the simulation that you're going to do this afternoon. And that is an approximation, so it's not going to match this exactly, but I just thought it would be good to give you some idea of what's going on and what some of the constraints are and the things that you will be thinking about this afternoon. So this was in 2019, the law was established, and then it took a couple of years to figure out how they were going to do this. And so we are moving forward with our climate action plan, way behind schedule, but we are still moving forward to it. So the idea was to move to a path of carbon neutrality statewide, and it will be mostly electricity because we are decarbonizing and electrifying, but by 2050. So that was the goal, carbon neutrality by 2050. So clean electric grid, so that's the decarbonized part. Energy efficient homes and businesses, right? So just using less to still cook our meals, turn the lights on, operate our computers. Clean and reliable transportation. Most of the transportation is gasoline, and so transportation is the biggest greenhouse gas emitter in New York State. And a clean economy for everyone. So thinking about climate justice and environmental justice so that not just the rich communities get the clean power, but all communities do. So this is what the politicians do, right? They come up with these great numbers, and then everybody else has to figure out how to do this. So 85% reduction in emissions below 1990 levels by 2030, or 40% by 2030, 100% zero emission electricity by 2040. And so this was like five years old or so. Lots of renewable energy. We are not on path to hit 70% by 2030. And that's broken down into a lot of offshore wind, distributed solar, storage, and energy savings. So that's efficiency. So that's a lot of change. Just so this is the decarbonization is all the stuff in the red square, and the electrification and efficiency is what's in that green box at the bottom. Yes.
Data mentioning about installed capacity or the electricity that's generated.
That's my next two clicks. I will get to that question. This is megawatts, right? So a watt is a rate. So this is the capacity, installed capacity. And I will get there in just a moment. So just this year, the governor of New York said, this is not going to cut it. We need also 1,000 megawatts of nuclear by 2040. So that's why we just had this big nuclear forum at Clarkson, because the nuclear will be up in my neck of the rural state, probably. And you need that for reliability, right? So is your electric grid reliable, like in the really hot in the summer? Yes, so it always is on. Whenever you turn the switch, you get, yep, okay. So progress has been made there, right? And no brownouts, or because the demand in power, electric power, the demand and the supply have to match almost instantaneously. And some of that supply can come from batteries or storage, but it's got to be instantaneous, or the grid, you don't have the right amps, whatever amps are. You don't have the right amps on your, on the grid to make it reliable. And so nuclear is on all the time. It's always there, because solar and wind vary a lot, right? It's really hard to build a reliable grid just on solar and wind. And storage is nowhere near ready. We've got batteries, but the batteries that they're installing, this does not say that they're like 3 to 10 hour batteries, right? That does not give us like a week of gray days if we don't have enough solar. So the very short time frame on the battery. So the battery storage is not sufficient. It's not long-term. And that's why hydrogen has some value, because you can store that for a long time. We just learned that. All right, so that's 1 gigawatt of nuclear. So the key is that this is the installed capacity. This is if everything was on all the time at 100%, we could add those up. But this is power. Power is a rate. It's like turning your faucet on, right? You can turn it on a little bit or a lot. Solar, you do not get 6,000 megawatt hours of solar every hour of the day. You might get it on noon on a very sunny day, but only then. You certainly don't get it in the middle of the night. So this is installed capacity. What we really need to track is energy generated. So you have to multiply that power times time and at some capacity factor. Like solar, it might be 27% of that 6,000 megawatts is really sort of the average what you actually get. So the installed capacity doesn't really answer our question is, do we have enough energy, which is part of the challenge with these laws. So this is what's going on in New York State. It's the path line as of 2021. And so the squares in green, those are our efficiency and electrification. You can see here heat pumps, electric vehicles, building envelopes, improving building envelopes, and then the squares in red, that's the renewable energy. And so we have truly renewable, And then we have ZEE is zero emissions electricity, which also includes large hydro and nuclear. And so that is coming on play too. And you see we get to net zero by 2025. And there's also regrowth of forests in here. So there are other things in here as well as just electricity. This is a plan for substantial the transformation, right? This is not just an energy transition, it's a transformation. It's a radical transformation over a relatively short time frame. But I think we can do it. So one of the biggest challenges in New York State, so here's a little bit of New York State. New York City is right here. This is Long Island. And I showed you a picture before. I live somewhere about right there. So this is the St. Lawrence River in Canada is north of that. These lines, except for that light green line, are transmission lines. The problem is New York City is the biggest consumer of electricity, but they don't generate that much. And so there's a lot of generation in the rest of the state, including some proposed, and hopefully they will still get built. Some important people in the country don't like the look of offshore wind, so that might get scrapped. But that's really important. And offshore wind is right near New York City and Long Island, which is where the demand is. So it would be great to have that offshore wind. There's a lot of land-based wind and big utility scale solar going in, but it's a much slower rate than what we really need to meet the goals. So those lines are really, really important. So this transmission line right here was just upgraded. We have hydropower, solar, wind, and now we're talking about nuclear up in this sort of, this is the most rural part of New York State. That we generate it and then it all gets shipped to New York City. And of course, some people like, why don't we get to use that in our region? We're generating far more than we need in our region. Another new thing that's just been going on the last year, there's a direct transmission line from Hydro-Quebec, which is hundreds or maybe thousands of kilometers north in Quebec, all the way through Quebec, all the way to New York, through to New York City. It's going through, there's a lake right here. They're putting the power line underwater. So it's going underwater so they don't have to build more land base. You don't have to worry about not in my backyard. Is that something that you're familiar with, a term? Okay. Not in my backyard is a challenge for these big solar and wind problems because you can see them. But I'd rather have one of those big in my backyard than a coal or a natural gas fired power plant. And then you have to breathe all the, deal with the air quality problems. So the key here is getting electricity to New York City. And that's what, because the generation in New York City is all, that was this I showed you earlier, this is all natural gas. But most of it's imported. So it comes from all directions, imported electricity, because in New York City, you have to match supply and demand. But there, the supply comes a little bit from their own generation, but a lot from imports. So lots of solar, wind, nuclear, hydro, upstate. Long Island is also completely natural gas, that they don't have any really renewables, but that's also the benefit of that offshore wind. So a lot of change, a lot of constraints, but getting the electricity to where you need it is really critically important for a reliable electric grid. Any questions on this? So I work with a lot of electrical engineering professors and students who, that they're real, like, how do you integrate all this distributed wind and solar in a way to still keep the system reliable? Because the solar and wind is very intermittent and it makes it not reliable. And that's the nuclear will help with that. Battery storage helps as well, but we do not have yet the technology, at least in an economically viable manner, that is longer term, longer than like the 3 to 10 hour storage capacity. New Yorkers pay more for everything. It's expensive to live in New York City. I don't know what you should, uh, electricity costs vary tremendously across the state. So right next to the hydropower plant, just 20 miles north of us, they pay um, less than half of what we do 20 miles away, because there's sort of the environmental services of having a dam in your river. So they get an economic benefit because of and that's true for a lot of like the utility scale solar that's getting built. Maybe you still pay the same amount of electricity, but they're paying what they a payment in lieu of taxes. So, but they're giving money like to the school system. So the school systems are improved. So they've got to be benefits, some financial benefits for the community who are having these large generation facilities. What? The payments. Yeah, yeah. And those stay in the communities where the generation is, not going to the state. Right. So it's an environmental justice issue. And I don't know if there's um, lower income people in that region, right? So it's an environmental justice issue. And we have the same challenge here in New York City, where those natural gas power plants are in the poor and communities of color. There's definitely environmental justice challenges in New York State, not just for the energy systems, and that's one of the things that this new climate law is aiming to correct, is to make sure that it's not just the poor communities that are accepting all the social and environmental inequities. All right, that was my overview of energy. Hopefully, because it's an important part of a life cycle assessment, at least understanding something about how energy is used, what the critical variables are. Efficiency is always key. And that goes to the efficiency of the use as well. If you're manufacturing something, if you can do it more efficiently, whether it's material efficiency or energy efficiency, that greatly can reduce the life cycle impacts. So actually, when I was here in 2019, we were talking about energy and more for air quality. It was a public health workshop, and we were doing a lot. And at that time, I thought India was working really, really hard on improved solar, right? Rapidly, but still, you got a long ways to go because of the amount of coal that's used. And it depends upon your region, right? So do you have so you probably have much better annual solar irradiance than in Potsdam, New York, right? Being much closer to the equator, drier. Maybe some regions of India, solar wouldn't be so good because it's rainy or cloudy. So maybe other areas are very windy. I changed my mind maybe about 8 years ago about nuclear. I used to think no, but the reactors now, I had a conversation, our colleague from the Navy is not here. We were talking about nuclear reactors on Navy ships and submarines. They've been doing that for decades, since the 50s, safely, right? Small nuclear reactors, right? Community scale, campus scale. It can be done. It might not be inexpensive, but it certainly can be done, and greatly reducing the greenhouse gas emissions with nuclear. So I've changed my mind about nuclear, that I am a proponent of nuclear when done well. And that's true for any of these systems, right? There is a right place and time and community to do it, and then there's less good communities and places to do any of these systems. But I think adding more renewables certainly would help. And one of the things about coal in India is more the softer, browner coal, I think, is my understanding about coal in India. And that has even more greenhouse gas emissions per gigawatt hours of, there's lots of different grades of coal. So the numbers I gave you were for the US, which is a much harder bituminous coal. If you've got softer brown coals here, then that is even worse for greenhouse gas emissions per gigawatt hour of electricity generated. And I don't know those numbers off the top of my head, but something to consider. All right. And that's being asked also about electrification as well, because when you electrify, then you need more batteries, right? Your electric vehicle and the battery storage on the distribution system. Then like the catalysts and the electrochemical reactions, those are the rare earth minerals. But then we also have steel, cement, so wind turbines, especially, they're getting bigger and bigger. They're just huge, but they generate, each one generates huge amounts of electricity. But that's why this one, why the toxicity is going up is because of that metal use with the renewables, that there are more toxicity effects with the metal use, ecotoxin in this particular case. And I've got other impact categories, but I just thought I'd show that, is that there are definitely complications from the metal use. So I think people have done for the batteries and for electrification that there's really just not enough of the rare earth minerals to electrify everything. I don't know about like steel, right? Steel is more of a basic, but it takes a lot of energy, and that's embedded in here, a lot of energy and a lot of mining to get the materials to make steel. So yes, very material intensive, but we will do less coal mining, right? So we'll be mining for different things. And some people who are dead set against batteries and battery storage and electric vehicles, oh, mining, we're going to have to mine for lithium and all these other things. Well, what do you think we're doing now? We're mining, extracting now. It's just we're going to be mining, extracting different stuff. So it's definitely environmentally destructive. Efficiency, right? Reduce our use. Just don't turn things on, and be more efficient with our use. Those are the most important things to do. And don't use AI if you don't have to. So what about the downstream side, right? So some of these things have, I think this is where our circular economies, right? If we can build them so the materials can be recycled and extracted, like the heavy metals in solar panels, then at least we can recover some. But the life of solar panels is far long, like you said, 10 to 15 years. It's really 30 plus years. The effectiveness goes down some, right? So you're going to get less electricity out of the same hectares of solar panels, but they still work. And so I don't think we want to rush to send them to the end of life if they're still generating electricity. We might need to supplement them with more other things. Wind turbines, it's mostly steel, right? So they are recoverable and recyclable, reusable. Maybe what's going to happen is that we use the same infrastructure and we just put new generators and inverters in them, right? As you know, so that's really what on a wind turbine, as long as it's structurally intact. And there have been some challenges with some of them, especially the blades are sometimes made out of fiberglass, and they can fail catastrophically. But mostly it's the electronics, it's the generator and the electronics that is what goes bad in a wind turbine. And so making them so that you can modular, right? Take those out, put a new one in, then that would help to reduce the end of life impacts for those sorts of things. It's something really important to consider. But again, that's one of the things that the naysayers for the renewable energy industry say, oh, we're going to fill up all our landfills. Well, we do the same thing right now. We've got abandoned, thermal power plants and abandoned coal mines. And it's not like we don't have end of life challenges with our existing energy infrastructure as well. This is not a new problem. There will be a lot of metals in it. And our transmission and distribution system will also need to get expanded, which is more metals, including copper, zinc, and things that have some toxicity issues.